So our first talker, it's Amit Barde, and he's from the Empathic Computer. Our first speaker, I'm sorry, it's Amit Barde, and he's from the Empathic Computing Lab at the University of Auckland in New Zealand. The title of his presentation is The Use of Spatialized Auditory and Visual Cues for Target Acquisition in a Search Task. Welcome, Amit. The floor is yours.
Cool. Thanks, Pablo. So can everyone hear me? All right. Great. So as Pablo said, my name is Amit, and I'll be talking about our study on the use of spatialized auditory feedback over a bone conduction headset with visual cues in a wearable device for a search.
Amit, could you hold?
Yep.
Could you hold
Yep.
for a second? Yeah,
Yep.
I think we had people in the other rooms, unfortunately, were giving sad faces, and I'll wait for Dustin to verify that they can hear the other rooms. Sorry about that.
Okay. No worries.
I think Dustin is in there now, probably restarting those rooms.
Okay.
I don't see him here. But I'll wait for his message.
Yeah.
Yes. Yeah. Okay, no problem.
Dustin, how are we good in the other rooms?
Let me check one more time, because he was Amit was on air, but he still wasn't showing up in the other room, so I'm going to go back and check.
Okay, one more check.
Do I need to make sure that there's anything on my side that I need to do on the host tools?
Just that you're on air, and Dustin just verified that you're on air.
Yeah.
For some reason, they weren't hearing you in the other rooms.
Oh, all right.
Yeah. You're all good to go, Amit.
Okay.
The floor is yours.
All right. Thanks.
Except, no, I'm sorry. Let's start. Sorry, Dustin's confirmation. He's
All right.
Yeah. Oh, sorry.
No worries.
Maybe you can still say something. I mean,
Yeah.
He says finally it's yeah. Okay.
Okay. And also,
Sorry
should
for
I?
the delay, everybody.
Yeah. Should I click the on-air thing on the slides as well on the browser so that you can see the slides advance, or I don't have to do anything?
No, don't worry
Okay.
about that. You just advance the slides.
Okay.
And you're ready to go.
Cool. All right. Great.
And then Pablo and I will both mute.
All right. Yeah. Cool. So, I'm good to go, right?
Yes, you're fine to go now.
Yeah. All right. Okay. So for those of you who missed the introduction, my name is Amit, and I will be talking about our study on the use of spatialized auditory feedback over a bone conduction headset, along with visual cues in a wearable device for a search task. So as you can see from some of the points listed on the slide here, a large portion of the research on spatial audio, there's significant research in the field of spatial audio for for the mobile environment, and a lot of the work focuses on the use of spatial audio as a means for information management on wearable devices. Shrinking screen sizes over the years have necessitated different methods to manage increasing amounts of information on such devices, but most of the auditory displays make use of headphones as a means to deliver auditory cues. Because of this, they may not be well suited to most real-world environments, such as, say, navigation in a motor vehicle, as headphones tend to isolate the user from the ambient acoustic environment, and it could prove dangerous in situations such as driving, and devices such as cell phones require explicit visual attention in order to gain any information from. So some of the proposed solutions, sorry, I'm on a different this thing. So we've chosen a bone conduction headset as we didn't find a large amount of literature outside audiology which dealt with bone conduction auditory perception. Another thing was I was also very intrigued by the possibility of using the Google Glass when I first tried them on as a better way of providing information to the users. The primary aims of this research, as you can see, are basically to help us evaluate whether the modes of presentation of information we've chosen are efficient. And in this case, the measure of efficiency is simply the time taken to complete a given search task. We also consider that this measure is a rough indicator of how much attention a particular form of presentation demands from the user. So the lesser attention it demands, the better it is. A secondary aim is to assess the usability of the system. So as part of this, participants were asked which queuing conditions they preferred, and things like self-rated speed scores, which means how fast they thought the queues that they used helped them find a particular target. From an application standpoint, we wanted to assess the applicability of bimodal wearable devices at being able to provide information for a search task. While the experiment I've described, that I'll describe here, is in a controlled environment indoors, I think the results have demonstrated that the use of a bimodal system such as the one proposed in this paper is feasible in a real-world environment. So coming to the background, there is significant previous research in the field of spatial audio for the mobile environment, and a large part of this focuses on information management for wearable devices. Shrinking screen sizes have necessitated that different methods to manage increasing amounts of information on such devices be implemented, and most of the auditory displays that are used for the purpose make use of headphones to deliver auditory cues. We think these may not be well suited for more real-world environments, such as navigation in a motor vehicle, because headphones tend to isolate the user from the ambient acoustic environment, which could prove dangerous in certain situations. And as I guess most of us already know, the use of a cell phone for navigation requires explicit visual attention in order to gain any information. So some of the proposed solutions that have come up over the years involve shoulder-mounted loudspeakers developed by Sony and Schmatz, and the integrated microphone on earphones used by Harma et al. There also been these solutions by companies such as Barde and Doppler Labs. But there are drawbacks to these systems that are mainly around the leakage of sound for the loudspeaker-based setup, such as the ones demonstrated by Sony and Schmatz. Researchers have reported issues with equalizations that need to be carried out for microphone-based systems in order to provide relatively accurate acoustic representation of the environments the users are in. They've also reported that wire and bone unconducted sounds such as eating cause a significant amount of discomfort for participants when using such a system. So the possible solution that we think for these problems with the systems that we've identified is using a bone conduction headset. So just a quick background on why we think the bone conduction headset is useful is one of the main things is it provides an unobstructed air conduction pathway for the ambient acoustic environment. So this also means that unlike microphone-based solutions, there's no calibration required in order to faithfully represent the ambient acoustic environment. And it also reduces the amount of sound leakage into the surrounding environment as is the issue with, say, shoulder-mounted loudspeakers. From a design standpoint, it seems to provide a relatively unobtrusive design that delivers both form and function. So for our experimental setup, figure A on the left shows the layout of the test space. It includes a door at the bottom from where the participants entered the space, and 6 tables in that space. Those 6 tables, there were 67 cards laid across those 6 tables. On the right-hand top, you'll see the signal flow. So the block diagram shows the signal flow between all the components used for the study, and tracking was achieved using 6 OptiTrack Flex 13 cameras that tracked a cap that was fixed with retroreflective markers that you can see in figure C of the participant. The participant was also equipped with a Google Glass and the Aftershok's Sports 3 bone conduction headset. The participants were required to find the target card that you can see in figure D. Card was placed face down to prevent participants from being able to acquire the target visually as soon as they entered the room. All targets tables were of all cards on all tables were of the same size. That was between 12.7 centimeters by 7.6 centimeters. The experiment utilized 2 types of stimuli. An auditory stimuli and a visual stimuli. So within those 2 types of visual stimuli were used, and I'm going to call them static and dynamic, and you'll see why. So the static visual cue consisted of a red dot superimposed on one of the rectangles that made up a basic map of the search space. And the dynamic visual cue consisted of an arrow that pointed in the direction of the target relative to the user's current heading. The distance to the target from the participant was also displayed in meters, and this information was updated in real time based on the tracking information. The length of the arrow changed depending on the horizontal angular distance between the participant's head and the target. The auditory stimuli consisted of a 1-second ping. 2 types of auditory stimuli were used, again, static and dynamic. So the static stimuli consisted of a sound source that was positioned at the target location and constantly pinged in the environment until the participant reached the target. The stimulus increased in volume as the closer and decreased as they moved away. This was a binaurally spatialized stimuli. The dynamic stimulus that was used was essentially the 1-second ping that was towards the target in a parabolic trajectory about 45 degrees from the participant's head. And both stimuli were binaurally spatialized using a plugin for Unity. The same sound is used for both the auditory stimulus. So for the experimental procedure, as mentioned earlier, participants were required to find a target card with a green dot on it. This card was placed participants from visually acquiring it upon entering the search space. Participants were guided to the target using the auditory or visual cues, or a combination of the two. The auditory cues were delivered over the Bone Conduction Headset and the visual cues over the Google Glass. So the experiment itself was divided into 4 blocks consisting of 9 trials each. For the analysis, the first block was set aside as trial considered during evaluation. All trials 40 seconds. So if a participant did not find the target in 40 seconds, the trial was ended. This was mainly done to prevent the experiment from going on for too long. All participants were presented with the same target location sequence, though the cues were delivered in a random order, and this was done to in an attempt to account for any distance that distance may have on the target card. It also to some extent helped us safeguard against the dependence of cue type and distance to target on each other. All trials began automatically once the participant entered the search space and the markers were detected by the camera. Following this, a cue was delivered to the participants, and once the participants finished the study, they filled in a post-study questionnaire. Target acquisition times, that is, the tables in the center and towards the rear of the room took longer entry. So to eliminate or to reduce the effect of the target's location, what we did was we averaged the time to find the target for each table for all cues. So this recorded response, the recorded response time was then subtracted from to obtain an adjusted value. So the results for these adjustments you can see in the graph on the slide. So the analysis of the auditory cue demonstrates that a significant difference between the search times for a static and a dynamic auditory cue, with the static auditory cue outperforming the dynamic cue. However, there seems to be no significant difference between the times recorded for the dynamic cue and the no cue condition. So this appears to suggest that cues, with the map cue, which is the static cue, significantly outperforming the dynamic cue or the arrow cue at the target acquisition task. The interaction effects between the different cues are pretty significant, but they seem to be greatly affected by the visual cue. This is especially true when considering the map cue. As part of our evaluation, we also decided to count the number of incorrect flips participants made during each. Good idea of how well the cues performed at directing participants to the target card. So the table there shows the average incorrect flips across all participants for all cue combinations. As seen on the table, the map cue performs the best across all cue combinations, and the arrow cue did not exhibit any significant difference either. The static auditory cue, as we said before, significantly outperformed the dynamic auditory cueing condition. At the end of the study, participants were asked to provide and the graph shows that participants appear to prefer the combined queuing condition. I should also, I think, mention that a higher score indicates a lower preference. There is no statistically significant difference observed between the visual and combined cueing conditions, however, but a significant difference does exist between the auditory cueing conditions and the visual and combined cueing conditions. Among the visual cues, participants appear to overwhelmingly prefer the map cue, while the static auditory cue was preferred amongst the auditory cues. A statistically significant difference between the cue between the cues within the cue types was observed. Participants were also asked to provide ratings on their own perceived speed scores. That is how fast they thought they found the target using a particular cue. And as you can see from the graph, the participants thought that they performed best with the visual cue, while the auditory cues do not appear to have instilled much confidence in the participants. As with the preference ratings, there appears to be no statistically significant difference between the visual and the combined cueing conditions. This appears to suggest a significant influence of the visual cue on the ratings. And as we've seen earlier, the results tend to reflect this trend as well. So some of the observations or insights based on the study that we carried out is that number one is our study has demonstrated that the proposed bimodal wearable interface is fairly effective at aiding a search task, at least in an enclosed space. And the results show that visual cues are significantly more effective than auditory cues at aiding a search task. And this seems to be especially true for the map cue that we used in the study. However, the static auditory cue proved to be useful when there were absolutely no visual cues involved, showing that there is significant value in having a cue, having an spatialized auditory cue. The map cue demonstrated the best results not only amongst the visual cue but overall. Also, it appears that it wasn't immediately apparent how the arrow cue worked to several of the participants. In the absence of the visual cues, the static auditory cue showed good usability and easily guided participants to the target. The dynamic auditory cue, however, performed nearly as badly as the no cueing condition, and participants found it hard to perceive the distance with any certainty. However, the dynamic cue did help participants orient themselves in the right direction. So besides these observations, there are some incidental findings that could play an important part in cue design in the future, and that is that several participants found the timbre of the auditory cue to be irritating. While we made every effort to design the auditory cue in accordance with some of the existing literature, I think more attention needs to be paid to this aspect to ensure better usability. Participants also appeared to monitor the arrow cue almost continuously during the search task, and this resulted in participants bumping into tables at times. The frequency of the bone conduction headset could have played a part in inconsistent spatialization experienced by participants, and it could have also resulted in spatial properties of the modeled environment not being fully conveyed via the BCH by the bone conduction headset. Some of the limitations we've listed here are one of the main limitations of the study is that we use commercially available spatialization plugin for Unity rather than any other standardized method such as HRTF databases. And we did not perform any kind of optimization. In particular, no equalization was performed on the stimulus taking into account the frequency response of the bone conduction headset. No physical alterations of the hardware were performed. Participants were allowed to put on the headset themselves, and we did not look to ensure that there was complete contact between the surfaces of the headset and the skin. As long as it looked like the participants had put on the headset in the right manner, we didn't intervene. This led to some leakage of the sound and possibly some perception through the air conduction pathway as well as the bone conduction pathway. But despite these limitations, we think the results we have obtained are encouraging, and some of the future research that can be carried out is mainly to identify the design learnings from this study and explore how these can be improved. And future studies must also attempt to incorporate things such as contextual awareness in such a device to be able to fully assess the usability of a device like this. The feasibility to switch between modalities for information delivery must be explored as well. For example, instead of displaying an SMS, it could be read out using a text-to-speech system or something similar. It will also be important for future studies to be run in real-world environments in order to fully assess how good a bone conduction headset and something like a Google Glass is at taking part in a search task. So thank you for listening, and I'll try to answer any questions anyone may have.
All right. Well, thank you very much, Amit. What a great presentation. We've got time for probably one question from the audience. So, if you want to raise your hand now, Amit.
Yeah.
Don't be shy. All right, I'm not seeing anybody raising their hand, and I think we need to get. Oh, Pablo. Let's. Pablo, you're on air.
Okay, so yeah, thank you, Amit, for your presentation. One question I have is that do you have any thoughts on how could you equalize or calibrate your your bone conduction headphone to ensure some sort of equalization problem?
Yeah, so there is a fair amount of literature actually that goes into some amount of detail on how bone conduction headsets can be calibrated for the frequency. We just didn't do it, and I mean the most I suppose the best way would be you tend to see sort of a band pass type behavior with the bone conduction headsets, where the highs and lows don't come out as well, and it tends to sound tinny. And so when you do the equalization, you're going to try and sort of make sure that these frequencies are to some extent come through in a better way, so that spatialization, the perception of spatialization, doesn't suffer.
Yep. Okay, thank you.
Yeah.
Thanks for that question, Pablo. All right, seems like we're at time. We need to move on to the next presentation.
Cool. Thank you.
Hi, Casey. I hear it's a bit soft. Do you have your amplify my voice on?
How's this?
Yeah.
That's better?
Yeah, that's great.
Okay.
Okay.
I'm just trying to remember how to set this up.
Is that your your talk.
Are you using the NVR browser or a separate device?
I'm using, I think, the NVR.
Okay.
Are my slides up?
Your slide deck is up.
I can't see them here.
Are you looking at the main screen or at your NVR browser?
NVR.
Okay. Do you have the slides link in there in your NVR browser? And if not, it might be better to do it on a separate laptop or another device if you have one.
Okay, I have it now.
Yeah, you just advance to the next slide. It looks like on the screen.
This should be the, yep, the title slide. There we go.
Great.
Okay.
Let's just for 1 second. I know we're running a little bit late, but I just want to make sure from Dustin. Dustin, are we okay in the other rooms to start this paper?
I believe so, yeah.
Okay. All right. Your introduction then, Pablo. Thank you.
Okay, perfect. All right, so our next presenter is Casey Collins from the University of Waterloo. And the title of her presentation is Realistic Audio AI, Spatial Sound Modeling to Provide Non-Player Characters with Sound Perception. Casey, go ahead. The floor is yours.
Thank you. Do I need to go on air?
Yes, you need to go on air.
Okay. Okay. So this, I think we're good. Okay, this work is based on the PhD thesis of a former student of mine, Brent Cowan. He wasn't able to present justice, and I may not be able to answer all of your questions, but some links are provided at Brent.
Casey, sorry to interrupt again. Would you also just check that you are on megaphone, which is amplify my voice on the host tool setting? Perfect. Thank you.
So the purpose of this talk is to outline what we found were some issues with existing NPC AI in games when it comes to sound and how we think we can improve that. So I will outline what the problems are and then discuss how we used Brent's spatial audio system called Graph to improve these issues without adding significantly to the processing cost. While we use Brent's system, the ideas themselves can apply to any spatial audio system. It's just that you are probably adding to the processing for reasons that I will explain. So I think that the points made are going to be useful for anybody involved in spatial audio rendering for games or sims, or involved in designing NPC AI. Most of us have played some form of game in which we interact with an artificially intelligent creature or entity, which are usually called NPCs or non-player characters. A lot of games use NPCs that attempt to find, seek, or follow the player character. Often this is done using pathfinding algorithms where if the NPC is in the line of sight of your character, then they see you and can come find you, follow you, whatever. That works fine with visuals, but what we found was that a lot of NPC characters have unrealistic auditory capabilities. In some games, the NPC acts as if they are deaf and they can't hear you. They can only see you. So you may be making very loud noise in an adjacent room and the character has no ability to detect you. Better NPCs have some hearing, but it's usually distance-based and doesn't account for occlusion. So a character might hear you through a wall where they shouldn't, or you're on a different floor and they can hear you because you're within a set proximity, but they wouldn't normally hear you if it were a real-world scenario. And finally, in the real world, there are acoustic phenomena that make it difficult to localize sound, and NPCs have unrealistic hearing capabilities because the system doesn't account for these phenomena. For instance, in Fallout 4, explosions can't be heard through the walls by NPCs, but in the real world, of course, that doesn't make sense. You would probably hear and feel such vibrations. So why is this the case when so much attention is paid to other aspects of the AI systems? Part of the problem we think has to do with the way that spatial audio is rendered in virtual environments. A lot of spatial audio systems are using ray tracing, beam tracing, and other pathfinding methods which become computationally expensive when having to account for, say, 10 different NPCs in a scene. A lot of spatial audio systems also don't trace the path of sound propagation, so can't mimic real-world sound localization. So what we mean by that will become clear in a few minutes. Brent Cowan built a system called Graph, which is a graph-based spatial audio rendering framework. And I'm not going to go into the details of the system because it's not entirely relevant to the point we're trying to make today, but I'll give you a brief overview so you understand how this can be done without adding to the processing costs. Essentially, rather than using the game's polygons, the virtual environment is converted into a simplified three-dimensional graph. So it's basically kind of simplifying a voxelization at a low resolution and creating a three-dimensional map of that space and then approximating the space using those kind of voxels or 3D graph. It works with FMOD and uses a GPU-based parallel processing and accounts for some of these natural ambiguities that happen in localization, which I will explain in just a moment. For instance, you can see here a two-dimensional map of a space. You can imagine it could easily be converted to 3D. We're just using 2D here for simplicity. By having sounds activate nodes in the graph, we can trace the propagation of a sound through space with occluding factors accounted for. By occlusion, of course, we mean a barrier of some type between the sound and the listener. So walls, windows, trees, vehicles, even very large creatures, and these are often omitted when calculating spatial audio. These types of objects will generally let some sounds pass through, but block others. So that's what we're talking about when it comes to occlusion. We ran tests on the system and on users, and we found that this method of processing sound was computationally more efficient, that it could simulate diffraction and occlusion more accurately than current systems, and was more effective in terms of how end users could perform in a space that required them to. So we ran tests on different systems and had users navigate a three-dimensional space looking for sonified objects, and we timed them. The results of that study were just published in IEEE Transactions on Games. The graph here on the right, you can see we compared, the blue line is the graph spatial audio system that was compared with a raycast method with occlusion and with a simple amplitude pan. We're able to navigate the space more quickly with the graph audio system. Brent's system, as mentioned, was designed to work with FMOD, and he's available for consultation if you want to talk to him about how to implement some of these ideas. While building the graph framework, it occurred to us that if we're already calculating the data to give the listener accurate information about the space, can hear. Simply put, the amount of sound energy lost by sound along a pathway is the same from A to B as it is from B to A. And we can use the same information we are already using to calculate the perceived direction for the NPCs. Now, a caveat, of course, it's not quite as simple as inverting the path. Perceived direction is usually based on the last leg of a sound's journey in the propagation or the last obstacle, so it's not quite as simple as inverting. There's lots of great formula in the paper if you want to consult how we approached that particular issue. Taking that idea of using data we're already calculating, and in our case calculating very efficiently, how can we improve NPC AI performance when it comes to sound? And these are the things that we thought could be adapted by other systems. However, you have to look into your own system and determine how much extra computation that's going to cost you. Okay, the first issue relates to a number of things we're going to put under the umbrella of environmental factors. One issue is that currently NPCs often just follow an ongoing sound. They can't think ahead. So you can imagine an animal that's tracking prey. The animal should be able to determine not just where the prey is now, but where they're going to be based on the directionality of their movement. A good AI needs to be able to think ahead. They should be able to estimate where a sound came from, where it is headed, and travel to that location and begin a search from there. Some NPCs do this, but the estimation is weak. A good estimation should require understanding where a influence the ability to determine where a sound came from. The frequency of the sound determines our ability to localize that sound. The ratio of direct to reverberant signal and the reverb itself can provide information about the room. So if an NPC knows a space well, they should be able to determine which room a sound came from based on the knowledge of that impulse response. And of course, we as humans do this unconsciously. I have a basic understanding. I'm currently upstairs in my office. If I hear a sound coming from downstairs, I can pretty much guess if that sound is coming from my living room or my kitchen based on the reverberation involved. So the characteristics of a room influence that sound, and a good NPC should have similar capabilities if it's in a familiar space. Another issue relates to audibility. NPCs now usually have either seemingly no hearing capability or have perfect hearing. So a good NPC system should take into account a number of factors. How good is the NPC's ability to hear? They need to be able to suffer temporary hearing impairment, for instance, if they just walked by an explosion or a gunshot, or they may have some damage that influences a permanent reduction in hearing. How well an NPC can hear a sound should be accounted for, and that includes how much attenuation of the sound is occurring, what the distance is, what the environment is, how much occlusion there is along the path. All of these things should influence the NPC's ability to hear. And then finally, there are known localization errors that we experience as humans that aren't, to our knowledge, accounted for in current systems. I mentioned already some factors that make localization difficult, including reverb, occluders, frequency of the sound, hearing ability of the listener, and the loudness of the sound. We also have difficulty localizing sounds in specific locations due to the binaural nature of our hearing system. Sounds directly in front or behind get confused because of the lack of difference in the interoral time delay, the level delay, and so on. Our system factors in a number of localization errors, including those caused by, for instance, if there is a sound source here on the right of the slide that is not traveling along a direct path, but is, say, down a hallway and then towards a listener, the listener may incorrectly perceive the source direction. Another example is a sound directly behind an occluder where the path to the listener may take an equal time, thereby confusing those interoral level and time differences that should occur naturally to help localize the sound. Another example, if there are occluders and reflective surfaces in a space that alters path direction, the NPC should get confused about the localization. We created a weighting factor that can factor in these types of errors and give a kind of confidence level for the NPC, the NPC's AI. So again, there's lots of formula and descriptions in the paper that goes into a lot more detail about how we did that. Effectively, the lower the weighting, the lower the confidence level of the NPC, it should take them longer to search a particular area. They may want to search a wider area than if they have less confidence. So summarizing the main solutions we propose then, when it comes to using line-of-sight pathfinders, we instead give occlusion factors to objects and provide more realistic calculations of environmental influences on sounds. Distance-based hearing rather than occlusion-influenced hearing, we calculate the occlusion's influence on those sounds. And the ability of NPCs to know where a sound is coming from is often unrealistic. We account for localization errors and provide a confidence value that can influence the AI to, for instance, have to search a wider area. The takeaway then is that audio-based AI behaviors are currently unrealistic and could use some improvement. We can use the data we're already processing, depending on the method used to render spatial audio, in terms of sound propagation to create more realistic behaviors without adding to the computational cost or the complexity. We already have to generate to create sound for the listener. We can use that same data for the NPCs. We recommended 3 main areas of improvement, and they were accounting for environmental factors, audibility, and localization errors, which could be adjusted based on the NPC's shape, their physical shape, ears are located on their body, how many ears they have, and what their hearing capability is. And by doing so, then we can create more realistic NPCs. We can do this without costing the team any budget in the processing. We used Brent Cowan's system, which worked with FMOD, but these same ideas can certainly be implemented into other systems. We just didn't look into the cost of additional processing, so it depends on how you are rendering your spatial audio. There's a lot more detail in the paper if you are interested. We also have, as I mentioned, published a paper recently that outlines the system in more detail, linked on the slide here, and even further detail and all of the code can be found in Brent Cowan's PhD thesis. Thank you.
Okay, I think we have time for a few questions.
Okay, it looks like Pablo has a question for Karen.
Yeah, so from the localization errors that you were mentioning, was it a particular group or type of localization error that was more, or that you think it's more important than others?
I can't recall the details of what we did. This is going back a while now. I don't know. It's hard to say. In terms of game environments, we were looking really at simulations, and I think perhaps the biggest issue that I found was just this front-back localization, that when you're dealing with three-dimensional space, trying to account for if something is directly in front or directly behind, and those auditory localization errors.
Okay, thank you. Thank you.
Yep,
Crash.
thank you.
Do we have any more
Okay.
questions for Karen? I don't see any more, so
Okay,
I think it's
thanks
time
very
to
much.
move to the next. Yeah, thank you, Karen.
Thanks, Karen. It looks like Pablo disappeared for just a minute here. He might just be re-entering. So, yeah, let's thank Karen again for their presentation.
Thank you.
Thank you. Hi, Joe. I'm going to get your slide deck up. You just take a few minutes here. We have time. Yeah. You can enter the stage though if you like. Yeah. I think you should be able to. Yeah. There you go. Yeah.
Hello everyone. Can you hear my voice? And okay, thank you. And I can't find my the web page in the menu.
Oh, okay.
Yeah.
So are you using the personal browser, the NVR browser?
No, I'm using Oculus right now.
Right. But then that means that you have to be using your browser inside VR, right?
No, I can't find any browser. So
Okay.
it should be located the Go Home section. Oh,
Yeah,
mirror.
it should be. Yeah, it should be between the home and the it's at about 10 o'clock on the compass menu,
Yes.
but you don't
No.
see it.
No.
Okay.
I don't see it.
It happens with some devices. The issue of the internal browser sometimes disappears. So we're going to reset the space and see if it comes back. Okay.
Okay. Now I can see.
Ah, good.
Okay. Let me open the browser. Okay.
Okay.
Do you find it?
Yes, I found.
Good. And then
And
one other
then
thing, if you could
Yep.
go to your host tools and then select go on air and also then amplify my voice.
Okay.
Can you guys hear me?
Yeah, so go on
I
air,
did
it
it.
should be in the middle,
Okay.
and also amplify my voice.
Yeah, I checked.
Did it? Checked? Okay, excellent.
Yeah.
And then
Okay.
let me, Pablo, before we do the introduction, let me just check with Dustin about the other spaces. And I think he's out. He's probably resetting those other spaces. We do have another 5 minutes anyway until the start time. 4 minutes.
Okay.
So we'll just wait a few minutes.
Okay. So actually,
try?
my
What?
cat's just running away. But I pretty right.
Well, why don't you? Yeah, why don't you try advancing one slide and then go back one slide just to make sure that's
Okay.
working.
Okay.
Yeah. Yep. Yep. Okay. It all looks good. And I just got the message from Dustin that it looks like the other rooms are okay. So now we just need Pablo back. Pablo has disappeared
Okay.
Yeah.
because here he is. Yeah.
My app is crashing. It's,
Okay.
It's like the 5th time, but hopefully
Sorry.
now it's gonna work.
Yeah. Just check your go on air and amplify since you came back in, and then just go ahead and introduce Joe here.
Yeah. Now I'm on air and amplified, I think.
Good.
Okay, great. So welcome to our third talk. Now we move to mics and speaker arrays. Our next presenter is Yosuke Tanabe, and this is a joint work between Hitachi and Tokyo University of the Arts. And the presentation is entitled Tesseract Array of Group-Based Spatial Audio Capture and Synthesis. Welcome. The floor is yours.
Okay. Thank you very much for the introduction. I'm very happy to present here. And thank you, coordinator, for arranging this very challenging and exciting event. So today I'm going to talk about Tesseract Array for group-based spatial audio capture and synthesis. So let me introduce the background of our research. So we are aiming to make the AR/VR system for acoustic design, such as the interior sound of terrain or appliances sound in the living room. So these are the one of the our business. So to do this, so we need to make the homogeneous system which where direction of sound is preferably treated as Marham discussed. It means so then we can in various way like we did, like we are doing, and in response to our movement, we can interact, and then so the spatial audio rotating and reflecting. Okay. So I think many systems employing the spherical function-based system like ambisonics. But now here I propose a system which is based on the symmetrically tesserated field, like this. So we basically pack the field and with the sphere as dense as possible to such a dense space, and I think we can't imagine in this COVID-19 situation. But in reality, so the acoustic field is something like this. So and this structure it's called tesseract crystal array. So that's why we called it tesseract array. So, but now let me simplify the diagram to express my the idea. In the audio capture, we capture the signal arriving from the sound sources to the listener. by a directional microphone array, which is located surrounding the cell. And then, for spatial audio synthesis, we play back recorded signal to the listener by the loudspeaker array, which has the same similar geometrical nature. And one of the advantage of system able to rotate and reflect sound without encoding and decoding. For example, the rotation of spatial audio, it is easy to rotate the signal, just rotating signal assignment to each loudspeaker like this. And for reflection of spatial audio, since there's because of symmetrical nature, there's a lot of reflection plane, and we can reflect signal assignment to each loudspeaker, which enable to reflect the sound. But so far, I mentioned all is about discrete scene. So there is some one of the challenge is to make this rotation and reflection in continuous way, so which I will discuss. I will talk next chapter. So okay. So here I employ the how can I say, the hexagonal array for simplification of my presentation. So since our model, our method is very similar to the classical amplitude panning, but using the group method, group theory, we called it group-based amplitude panning, in short, GPAP. So now, in this array, the spatial audio is composed by 6 signals, S1 to S6. And there is 60 degrees of rotational operation called C6 on Z-axis. So we have 6 discrete bases of rotated signal, which is identity, and C61S, which means operated C6 operation once, and C26S means operating C6 operation. So the spatial audio for a given rotational angle can be given as the weighted sum of 2 of 6 bases, as shown in this equation. And here, G1 and G2 is the weighted function calculated by tangential panning law. Okay, next I will talk about reflection of the spatial sound. So hexagonal array, there's 6 reflection operators L. So we have 6 bases of reflected signal, such as sigma 0s, sigma 1s, and so on. Let me show the simple example of the system, a simple example of the reflection, assuming the signal reflected by the reflection plane, sigma 0. Now, then, the reflected signal is given as the signal itself plus n-sample delay of reflected signal. And sometimes we use reflection coefficient R to apply the damping, offensive, and so on. And applying G to the reflected basis realize the reflection of the plane for any given angle. So this is the heart of our system. Okay, next I will talk about array. The geometry. The geometry of tesseract array consists of 2 polyhedra. One is cube octahedron having 12 vertices, and other is dual spherical rhombic dodecahedron having 40 boxes. And as I mentioned, our system is based on the closed sphere, and it's directly related with cube octahedron. Rely on the visual planning. We need to place the loudspeaker as dense as possible, keeping the geometry the same. So that's why we we employ the dual structure, dual polyhedra called spherical rhombic hydron. Anyway, in short, there's 26 channel microphone or loudspeakers. And this tesseract array belongs to octahedral symmetry called OH. And there is 48 discrete bases in total. And there is 24 rotations, which is shown in the left. And there's 24 reflections, which is shown in the right. So we can synthesize a variety of sound spaces as the sum of these 48 bases. Okay, so next I will talk a little bit about physics point of view. So in the left, I show a physical model of our system. Here, the sphere now it's called the yeah.
Just reset the space because we were getting some audio glitching, and I think you sound better now.
Mhm.
Yeah.
Okay. So I'm happy to welcome back this virtual space. And I hope my cat coming back. And please give a moment to reopen this web. Okay. Okay, so now we are in the physical background of tesseract array. So as I okay, thank you. So as I said, so physical. So there is we modeling the space as a mass and acoustic compliances, and so acoustic element consists of acoustic inertia on the surface and acoustic compliance, which connect the adjacent acoustic element. And sound pressure can be evaluated at the center of gravity of acoustic element, and particle velocity is evaluated as a motion of acoustic inertia along the acoustic compliance line. This is very intuitive model, but it's good enough to make the wave equation, derive the wave equation as shown in the right. So on the top, I show the continuous equation, and it says that sound pressure P become as a weighted sum of particle velocities. So in this sense, we can say our system for spatial audio synthesis relies on active intensity concept, which is discussed by already. Okay. Oh. Wait a moment, please. Okay, but our model, our system may be possible to reproduce the wave motion exactly when the wavelength of the sound is longer than the array size. Here I show the analysis result of eigenvalue of square room using the tensor array structure. So in this condition, analysis corresponds very well the value from the theory. Okay. And next, I will talk about the prototype of Tesla microphone array we built in our laboratory. We placed the directional microphone on the vertex of two polyhedra, and these microphone along the vector line of particle velocity. And as Sena discussed, we need to minimize the crosstalk between non-adjacent channel for intensity-based system. But sometimes it's difficult to realize this. It's very hard to find the microphone to meet this requirement. So far, we are using supercardioid microphone. And to overcome this, so we make the microphone array relatively larger. So right now, so the diameter of the array is 6 to 700 millimeters. But it's big, but it's good enough to locate the omnidirectional microphone at the center for absolute sound pressure capturing. This value can be used to equalizing the sound space or adjust the level to the real environment. And it is good to note, so this system is compatible with spherical-based functional system because this is a spherical shape. It means so we can analyze the recorded signal via the spherical harmonic functions, like for ambisonics. Okay, so finally, I will talk about the Tesla loudspeaker array installed in the anechoic chamber. So there is 26 channel plus LFE in total, and in the top layer, there is 9 channel, and each channel is located 45 degrees interval in azimuth angle. On the top, there is top center for voice of God, so-called voice of God. And the middle layer, so there's a channel, and again, so the 45 degrees interval. And the bottom layer, so there is 9 channel plus LFE, and 8 channel is again the 45 degrees interval. And on the bottom, the grating of the anechoic chamber, there is bottom center for voice of hell. Okay, so and this loudspeaker inward at the sound pressure sampling point, and we can I can say it's almost compatible with existing channel-based system like a 22.2 multi-channel, Dolby Atmos, or 3D, except these system place the FL front left and front right at plus minus 30 azimuth. I think it's almost same, I can say, maybe. Anyway, so and also it's compatible with spherical function-based system. Of course, it's a spherical shape. Okay, so now let's conclude my presentation. So first, we proposed a microphone and a loudspeaker array for homogeneous acoustic experience. And then we formulated the rotation and reflection of the spatial audio based on the nature of symmetry of the array, which enable the system without encoding and decoding of spherical function. And we constructed array based on cube octahedron and the spherical rhombic dodecahedron, which belongs to the octahedral symmetry group, having 48 discrete bases. And using these bases, we could simulate, we can synthesize the variety of sound as a summation of these bases. And finally, we demonstrated we just showed the prototype of microphone and loudspeaker array. Okay, that's all of my presentation. Thank you very much. Thank you. Thank you.
We have plenty of time for the questions, so please go ahead.
So click on your hand raise button, and once you do, we'll let you answer your question. All right, Pablo, you're on air.
All right. If I have a question for it's for both the microphone array and the loudspeaker array. Could you talk a little bit about how do you calibrate these arrays?
So what do you mean the calibration of the array?
For example, for the loudspeaker array, do you need the loudspeakers to have the same frequency response at a certain point in space?
Yes. So yeah. Okay. So yeah. So we did calibration. So actually, so we are using a generic loudspeaker array system, and we are equal at the center of the listening point, and flatten and make the flat response from each loudspeakers. And also, we equalize the synthesized sound based on the recorded data of Omni microphone data. So so because we are using the directional microphone, and the directivity is very depending on the frequency. And the total sound is not become the nature of frequency response of sound itself. So we need to equalize each sound coming to the center of the array.
All right. And just one quick follow-up question: is this calibration for both magnitude and phase spectrum, or you just want a magnitude flat response on your speaker array?
So in terms of time domain, so we are calibrating the delay of sound. I mean, so of course we are trying. Of course, the system itself is spherical, and there's not so much time delay, but we are equalizing at first. Then next step is equalizing the magnitude spectrum of the sound.
All right, thank you.
Any question or comment? So I'll present. I hope if I could attend a meeting next time. So I will present more interesting, more realistic demonstration result based on the system. So because COVID-19, we couldn't conduct much of experience during this term. So it's very hard for me to have a presentation like this. Okay.
Yeah, sure. Thank you. We understand that.
Any question? No comment? Oh, I need to amplify my voice.
Yeah, I don't see any other questions. Pablo's been the awesome keeping the conversation flowing in each of these sessions. But if anybody else has any more questions, please raise your hand and we'll get you up next.
Okay.
Or else Pablo can keep asking questions.
Yeah, I don't have any other questions for now. So yeah, it seems like we don't have any more questions. So I want to thank the speaker again. Thank you for your presentation, and thanks everyone for attending. I think we're wrapping up and finishing the 4-paper session. Thank you, everyone.
Thank you. Thank you. Thank you, guys.
And just another reminder that everyone's welcome to come over to AVAR lobby for more discussion.
Great point, Matt. Thank you.
That's cool. And thank you, Pablo, for the. All right. Oh, he's gone. Okay. Thank you, Matt.